So one of the things I'm really interested in my lab working on is self-assembly. And so you probably realize this, but you're not made in a factory, right? Like a mini car down the road in Cowley goes through this big complicated factory and out comes a mini. But you make yourself. That means you're self-assembled, so you assemble yourself. And I'm interested in that process, which is amazing. How on earth does that work? How do things make themselves? And of course, I want to study something simple. So what I study is viruses. And so here I'd show you some examples of a virus on a computer. Viruses are little shells, basically, made of the same component repeated many, many times. So in this case, this was made of 12 pentagons. And they're designed in such a way that if they move about randomly, using a Monte Carlo algorithm, they move around randomly. If you design them right, they move around randomly. In this case, 24 of these form 2 viruses. Over time, they go like this, like that, like that, like that, like that, and then boom, you got 2 viruses. And what's great about this is that these are computer viruses, so they've designed on the computer. But we figured out how to make the interactions in such a way that no matter how we start them, no matter how we wiggle them around, they always form the same shape at the end. It's a little bit like taking Lego blocks, putting them in a bag, shaking the bag, and out comes a fully formed train. In fact, if I could do that, I'd become very rich, I'm sure. So that's what nature does. And on the computer, we're trying to understand what the basic principles are, the physical principles that allow you to this process to make things from just randomly moving around. And there's a really interesting link there with evolution, because people often think of randomness as being purposelessness. But in fact, we use random movements, like these movements of these particles moving around, all the time, as a way of optimizing things. In fact, using random Monte Carlo algorithms to optimize very complicated problems is something you see all over engineering, all over physics, all over finance. The interest rate that you get on your bank account is calculated by some quants in the city, London, with a Monte Carlo algorithm, doing random calculations to figure out the optimum interest rates that they can give you. And that's how they price options, that's how they price stocks and derivatives. And so the idea that you use this random algorithm to optimize is something very well understood in the physical sciences. And so I think that evolution, in many ways, is the same thing. Evolution is a random optimizer, stochastic optimizer, just like Monte Carlo algorithms are. And it's probably the very best way of finding the solutions in biological space that we now call you and me.